increase the rigidity of the whole member, and we can make those with a Ti-6-4 very easily. We can bond the material together very easily. We can make body implants out of these kinds of materials. Most of the body implants that we use for high strength are cobalt-based alloys now. Back in history again, we used to make them with a stainless steel. Then we found out that the nickel was a little bit carcinogenic, and we didn't want any nickel in it, so we used chrome cobalt in these particular body prostheses now to put them in the body. And so this material, it's titanium, finds itself useful in transportation, in body repair, and in almost any place where we need the highest strength with the lowest weight. That's the material we would generally reach out to put our hand on, and yet the material has lots of little problems, and that is it's very reactive. It's extremely reactive, and unless you put it in a certain form and you want to put it in seawater, then you really have a problem. We'll talk about that when we talk about corrosion. Well, I want to touch one final thing now in the non-ferrous materials, because I'll be talking about copper in the next lecture, but I would like to touch for a moment on the ability of the materials to stay stable once we get them. Because we have this big problem that affects us all, and it is mirrored exactly in that prosthesis problem. Say for a stem prosthesis, hip stem prosthesis, we don't want to use something in our hip that's going to kill us, right? By the same token, we don't want to use it anywhere in our body if it's going to be toxic. We don't want to manufacture the materials if the operation is one that is of high toxicity or poisonous. And so, for instance, we find that one of the materials that we plate, a non-ferrous material that we will put on a ferrous-based material to protect it, will be cadmium. Cadmium, if you generate its oxide, which is very easy to do, it's a low melting point material, and if you ingest it in your respiration, get it in your lungs, it's pretty well guaranteed to kill you quickly. So we have to become concerned in looking at all of these metals and alloys, these non-ferrous metal and alloys, when we play with them, is what are they going to do to us? So let me tell you about one that you ought to ask yourself a question about. When you answer the question, it's going to teach you an awful lot of metallurgy. The question is, would I let anybody put mercury in my body system? Would you do that? And we all shake our heads no. Then I ask you, have you got any fillings in your teeth? And did you ever notice the way the dentist makes the filling? And he takes silver, a little silver copper alloy, and he mixes it with mercury, and he shakes it all up, and he packs it in your tooth. And the amount of mercury is sparse enough so that it diffuses into the solid metal, and we have developed a cement or an alloy that bonds a lot of phases together. But inside of every one of your amalgam fillings, you have a great big whop of mercury in your body. Now, does that bother you? Must not, because I'll bet you every one of you has a filling. Why doesn't it bother you? Well, one of the reasons is because you didn't hear anybody dying from having their teeth filled, right? Looks pretty good. Why not? It's because the mercury would have to escape from that system. And the saliva in your mouth, the media that it's sitting in, actually doesn't dissolve the mercury very well. But if it did, it would take the mercury from just the surface of the material. And now to get any more mercury into your system, it has to diffuse all the way through the filling and come back to the surface to be dissolved. Can't dissolve it from the inside very well. That process goes on at such a slow rate that at your body temperature that you wouldn't expect to have a lot of mercury accumulated or assimilated in your body over a long period of time. But how about other things that we would use, like aluminum ware? You know, drinking out of is aluminum poisonous? It's a very interesting thing to see. If you get the 1948 edition of the American Society for Metals Handbook and you look up poisons, you find out that aluminum has about 2 pages on poisoning of aluminum. And what it tells you is it isn't poisonous. That's the big result. Actually, on cadmium, there's only about 4 sentences, about that long. And it says, this is deadly poisonous, right? and there's even more on mercury and whatnot. But the situation is that a lot of what we think about metals comes from tales that we hear that are carried without going to a metallurgical source to find out what's really so about it. If you got the aluminum in your body, it would only go in your body as aluminum oxide, because that's immediately what aluminum turns to. If you cut a piece of aluminum with a knife, the score mark that you made within microseconds is aluminum oxide, the surface is. So it's almost impossible for you to get aluminum in your system without it being aluminum oxide, unless you got shot with an aluminum bullet or something. And aluminum oxide, if you read all of the little packages of medicine that you take, like Rolaids and Tums and whatever, you'll find that aluminum oxide is one of the things that you take if you need to settle your stomach down a little bit, right? So somebody once calculated how much aluminum that you would assimilate if you used aluminum cookware over, let's say, a lifetime, and compared it with how much aluminum you'd take if you took the medicinals normally given for the morning after the night before. And it says that one wild night would give you more aluminum in your system than you'd ever get from cooking aluminum all your life. So what you really need to do is go to a good source, but you shouldn't be ignorant of the fact that most metals have some toxic effect on you somehow. And so you ought to have a keen idea of what you're doing with all of these things if you're going to play with them. Well, the last thing I'd like to cover in this particular session is I'd like to talk about zinc, the refining of zinc and the use of zinc, because zinc is one of the most used of our metals, of our non-ferrous metals. And I noticed yesterday when I left to go back to the hotel, after I'd been talking about all these pretty crystals, remember, in the previous lecture, and I looked at a lamp pole out on the highway just after you leave Livermore out there, and you see these, not the ones that are painted now, but the metallic standards on which the lamps are. And do you know the zinc crystals are so big you can see them from the car, you can identify them. Once you've seen these things, you look in and they're that big, and if you don't see them when you go home tonight, you're in Amos, right? But we use an awful lot of zinc out there to prevent corrosion. We'll talk about that in the corrosion section. So let's talk about winning the zinc. The zinc is generally going to occur as a sulfide ore. So if you were in the business of making zinc and you had assayed your ore and found it's going to be economical to take the zinc out of it, then what you would do normally is to say, I want to get rid of the sulfur. You see, it's a simple system. As I described to you earlier, we are pretty sure that early man had lead sulfide and he just made a fire, and it transforms at such a low temperature, melts at such a low temperature that he drove off sulfur dioxide and that elemental lead left. Lead oxide is so easy to reduce with carbon that you can do that. If you heat up a pot of lead and get a dross on top that's lead oxide, all you really have to do is to drop a pinch of stearic acid in it, or a little bit of a plumber's candle, because the plumber always did this in that wiping joint situation, and the plumber's candle had a lot of stearic acid in it, and whoosh, like that, all of this dirt on the surface disappears and it looks like a pool of shiny mercury. Why? Because the oxide is so easy to reduce. So if we take the material that is zinc sulfide, we can now reduce it or put it into an oxide form to reduce very easily. Actually, if we just heated the zinc up to a very, very, very high temperature in the presence of oxygen, the material will drive off sulfur dioxide, but we will make zinc oxide. So if at the same time we incorporated in a little briquette that had carbon, or we put mixed carbon with it at the same time, we would drive off the sulfur dioxide, and we would have left in our hand zinc, molten zinc, lots of it. And zinc actually boils up around 1700 degrees Fahrenheit, and so it would be hot enough to want to be a vapor, but you could condense it in retorts and run it around and cast it and do all sorts of nice things with it, as we'll see in the next lecture. So it's pretty easy to refine. But if you were on the East Coast and had time, you should go to a place called Palmerton, Pennsylvania, which is just outside of Allentown. And you'd drive through that place, and look at the town of Palmerton, which is on your left, little town that sits there, and over on your right you see all of these mountains that are very close in, not far away like the hills here, but very close in the side of the mountain, and there isn't a tree, there isn't a blade of grass, there's nothing green growing on it. Now maybe you don't see green stuff out here like we do, but to see rocks sticking up out of the ground on the East Coast is rather unusual. And they have been that barren for 35 years. That's what it does. That's what acid rain is all about. And so we had to clean up this mess, because in the process you're going to generate something that's very, very damaging to the environment and to you.
Some substitutes for aluminum include beryllium, magnesium, and titanium. An important criteria for these materials is the ratio of weight to strength. Titanium has the highest weight to strength ratio, followed by magnesium and aluminum. Extraction processes for non-ferrous metals include reclaiming magnesium from ocean water and transforming titanium tetrachloride into elemental titanium. When alloyed with aluminum, titanium makes a very good material for military and commercial airframe construction. Examples of stable forms of non-ferrous metals include dental fillings that contain mercury and aluminum cookware. Zinc sulfide is easily refined, but the process is damaging to the environment.
Well, we'll have to continue to look at this now to learn more about these fabrication techniques or refining techniques, and so I'll do that in the next series.